session for CS61B. So let's get into some review. So first things first, let's talk about disjoint sets. Let me get my laser pointer. Okay, so for disjoint sets are basically a way of figuring out which items are in a set together and which items are not. And so there's two main aspects of a disjoint set. The first is connect, and the second is connected. Connect returns true if those two things connects two items, X and Y in this case, they tend to be numbers, and is connected returns true if they are connected and false if they aren't. Now there are 4 different kind of iterations of disjoint sets, each better than the last. So quick find, the idea here is that we use an array of integers to track which set each element belongs to. At the beginning, every item will be part of its individual set, and then as you go around, when you combine things, you are going to make each item you're going to combine the sets basically. And so whenever you combine 2 items or 2 sets, you're going to replace the number in that slot in the array with whatever new set that it's joining. Quick union, rather than storing the set number, stores the parent of each node. And in this case, what it's referring to as parent is one of the items that you're connecting will become the parent of the other item. And then the way you're going to check whether or not 2 things are connected is by seeing whether their topmost parent is equal. So here you would be checking to see whether or not they're part of the same numerical set. Here you would keep calling the parent of the node up until you get to the point where you're at like that root of this sort of structure. And if the 2 items have the same root or root great grandparent or whatever, in that case, then they are part of the same set, so they would be connected. Weighted quick union is the same thing as quick union, except it decides which set is merged by based off of which thing is larger. And so the smaller of the 2 sets that you're combining will become merged into the larger. And this basically, if you look through lecture and things like that, you'll see that it makes things significantly faster. And then lastly, weighted quick union with path compression. It's basically the same thing as weighted quick union, except now whenever you call is connected or connect, any node that you visit while you're doing those operations, you're just going to set the parent of that node to the root of that set. And that way it'll be a lot faster in the future, so this will take constant time when you are revisiting the same thing twice. So here's a chart that kind of showcases how each one improves on the previous. Moving on to trees, let's talk about minimum spanning trees. So minimum spanning trees are a set of edges that connect all the nodes in a graph while being of the smallest possible weight. So minimum is referring to the total weight summed up of all of the edges in that tree. Spanning is referring to the fact that that tree has to span all of the nodes. You can't leave any nodes out. And tree is referring to trees. So you can't have any cycles because it is a tree. It is important to note that MSTs may not be unique if there are multiple edges of the same weight. An example here is that in this situation, this MST is not unique because instead of having A to F in this MST, you could replace that with C to F. It would still be the smallest possible weight, it would still span all of the nodes, and it would still be a tree. There's 2 different ways that we get minimum spanning trees. The first option is Prim's algorithm. So you can kind of imagine Prim's algorithm as being kind of a node-focused way of getting your MST. So the way it works is that you start with one node, let's say with A, and you see all the outgoing edges from A and you pick the smallest one. So we're going to pick this A to C node right here. And now you're going to see all of the outgoing edges from both A and C. And by outgoing, I mean edges that do not connect to something that's already in our MST. So like this edge doesn't count, but we're going to look at all the other edges coming out of both A and C. In this case, we have 2 options, and we're just going to go based on the one that's alphabetically smallest. So we're going to pick A to F. And so that becomes part of our MST. And now we have A, C, and F already there, and we're going to look at all outgoing edges. At this point, CF is no longer an outgoing edge, even though it's also not part of our MST, because it would create a cycle if we were to add it to our MST. So we're looking at this edge DF, this edge AD, and this edge AB, in which case DF is the smallest, and so we're going to add that. And now A, C, D, and F are all part of our MST. Likewise, we have B and E, and so that are both of the smallest possible weight. We're going to go alphabetically first and pick B, and then lastly, we're going to pick E. And that is how we form our MST in this situation. Kruskal's algorithm is very similar. You can kind of imagine it more as an edge-focused way of getting your MST. Rather than starting in one area and kind of expanding outwards like you do in Prims, in Kruskal's, you're just going to kind of look at all of the edges at once and pick the smallest edge that does not create a cycle. So looking at this entire graph, we have 4 different edges that all have a weight of 1. So we can just go alphabetically and pick them. In this case, none of the edges will create a cycle, so we can pick any of them. So we can do AC, and then we can do DF, and then do DB, and then DE. It doesn't really matter. But what's important is that now we have all of these edges in our MST. So the next step is we're going to look at the next set of edges that are of smallest weight. So that'll include CF, AF, and BE. Now, we can't include BE because if we were to include it, it would create a cycle right here. So we know that that's not going to be our next edge. Like with Prims, we can pick either of these because, like I said, MSTs are not unique. So I'm just going to pick the one that's alphabetically smaller. I'm going to pick AF. And now in this case, we cannot pick CF because it would create a cycle. And if you notice, if you pick any other edge in the graph at this point, now that we've completed our tree, it would automatically create a cycle, invalidating that tree. So we are done with Kruskal's algorithm. Moving on from minimum spanning trees, let's talk about shortest paths. So minimum spanning trees refer to the minimum weight of a tree that spans all of our vertices, but that doesn't necessarily mean that they're going to contain the shortest path from every node to every node. I mean, a key example here, for instance, if this vertex if one of these was higher or something, so for instance, ACF, if CF was included in our MST rather than AF, which again would be a totally valid MST, then in that case, the shortest path from A to F would not be included in our MST because AF is shorter than going through C. So likewise, this happens frequently that the shortest path between two given vertices is not actually in our MST, so we have different techniques for finding those. The first is called Dijkstra's algorithm. Dijkstra's is a method of finding the shortest path from one node to every other node in the graph. So you're going to use a priority queue that sorts points based off of their distance to the root node, and then you're going to pop the top node off the queue, top referring to the smallest distance. And then once you've popped something off the top of the queue, that's set in stone because every distance after that is going to be larger. Dijkstra's only works on graphs that have only positive edge weights, which means that you know you're never going to end up with a smaller edge weight than what you currently have. So once you do that, you're going to add or update the distances of all the children of the current node, resort the priority queue, and then do the same thing all over again. We will have an example on the worksheet coming up, so if you're a little confused, don't worry about it. A star, unlike Dijkstra's, is a method for finding the shortest path from one node to a specific other node. So Dijkstra's gives you the shortest path from one node to every other node in the graph. A stars only gives you that shortest path from one node to a specific other node. Why might we do this? Well, for instance, let's say you want to drive from LA to New York. And on your map, you have the nodes are all cities, and the edge weights are just the distance between cities, how much time it will take to drive between those two cities. Well, in America, there are lots and lots and lots of cities, and so running Dijkstra's might take a really long time because you'd explore basically every single part of that graph. A stars, on the other hand, can be much faster because once you hit that endpoint, you're done. So the way A star manages this is by using a heuristic. In this class, we will always give you a heuristic. If you're interested in how heuristics can be developed, I recommend you take a class like CS 188. The best way to imagine a heuristic is trying to imagine kind of a map, like an overhead map of the US, going back to our driving example. Now, you can take a ruler out and measure the distance between cities and use that as a heuristic for how long it's going to take for you to drive from LA to Santa Fe, for instance. However, in reality, when you actually drive, some roads are slower than others, some roads have more traffic, some are windier than others. So the actual time it takes to take each road might be longer than the one that you have. So our heuristics must be less than or equal to the true distance from what node you're at to the goal node. The heuristic is kind of a guess at how far away the node you're looking forward to going to is from that goal node. So otherwise, A star works pretty much the same. You pop the top node off the queue, where that top node, rather than distance from your current node, it's distance from the starting node plus the heuristic, and then you add and update the distances of all the children, and then you resort and you keep going. Another difference is that you keep checking whether or not you've hit that goal node, and once you have, you're just going to stop. Okay, let's get some practice in for all this. I know it's a lot of content. So, starting with weighted quick union, draw the weighted quick union objects that results from the following method calls. I'll give you guys a chance to think about it. Okay, let's go over it together. So, this is what the result's going to look like. If you're confused why. So first we're going to connect 1 and 3, which is going to give us this kind of block here. We're just going to break ties in terms of the two sets we're joining are the same size by setting the smaller one as the parent of the larger one. Then we're going to connect 0 and 4, and likewise 0 is going to become the parent of 4 because of that same tie-breaking rule. Now we're connecting 0 and 1. So again, these are both the same size, so we're going to connect the set that has 1 in it to the set that has 0 in it. So we're going to connect the root of that set as a child of the root of this set. Lastly, we're connecting 0 and 2. All this time, 2 has been on its own as its own set. So and it's smaller than the set that we're joining it to, so it's going to join as the child to this set. So the parent of 2 becomes the root of the set that we are connecting it to. So, based off of this that we just got, what is the resulting array of weighted quick union after all these calls have happened? So what does the array of format version of this kind of conceptual data structure look like? I'll give you a chance to try it out. Okay, so coming back around, this is going to be our answer. The reason is the format we're using for the array here is that the size of so everyone points at their parent unless you are the root of the set, at which point you have a number that signifies the negative of the total size of your set, so that once we hit a negative number, we know we're at the root, and then whatever that negative number is, that tells us what the size of our set is, which helps us compare quickly when we are trying to figure out which item becomes which item's parent. So in this case, 0 is the parent. There's 5 items, so that's -5. 4, 1, and 2 all have 0 as their parent, so their values are 0. And 3 has 1 as its parent, so its value is 1. Okay, let's move on to minimum spanning trees. So the first thing I want you to do is perform Prim's algorithm on this graph. Okay, let's go over it. So the result here looks like this, and let's talk about why. So we're going to start with A just because of convention. And so looking at the outgoing edges from A, 6 is the smallest, so now B is going to be part of our MST. So the first edge we add is AB. Next, we're looking at all these outgoing edges. We have a 12, we have a 3, we have a 4, we have another 4, and we have a 7. Well, 3 is obviously going to be the smallest. We're going to add BC to our MST, and that's our second edge. Now A, B, and C are all in our MST, all the outgoing edges, 9, 6, 4, 7, and 4. We're just going to pick the one that comes alphabetically first to tie break between these two 4s. So we're going to include this BE edge. So that's our next edge. And now A, B, C, and E are all included in our graph. So our next thing that we're going to check is, again, the outgoing edges. So we have this 4, this 7, this 2, this 6, and this, or not this 6 because E is already in our graph, and this 9. So this 2 is the smallest, so we're going to add EF next. And now A, B, C, E, and F are all in our MST. The only 2 outgoing edges we have left are this 4 and this 9, both of which have to be included because they are the only edge reaching these nodes, and our minimum spanning tree has to span all of the nodes. So we'll do BG first because it's smaller, and then CD, and that gives us our completed minimum spanning tree using Prim's algorithm. This is the order in which you add all of these edges. This minimum spanning tree is unique because there are no edges of equal weight to the edges that we've added that are not in the graph. Okay, now do the same thing but with Kruskal's algorithm. Okay, so again, we're going to get a very similar result in terms of our graph, but the order in which we add things is going to be different. So looking at this graph kind of holistically, what is our smallest edge? It's going to be EF, so that's the first thing that we're adding to our minimum spanning tree. Next, we are going to look again. Now it's this BC, that's 3, so that's our next edge. Next, we're looking at BE and BG because they're both 4. The order in which we add them doesn't matter, but we're just going to go alphabetically. So first BE, then BG, and now we have these 4 nodes kind of set together, F by itself, and then D and A by themselves. So the next highest are AB and CE. We can't be adding CE because that will create a cycle right here. So AB is our only option. So that's our next one. And then lastly, we can't be adding BF because that will again create a cycle. So our next possible edge is CD. And once we've done that, we have connected all of our nodes and we can stop. So again, the same result as when we did Prims, even though that's not necessarily always the case, it's just the case this time. But the order in which we add edges and nodes is different when we do Kruskals. Okay, so now let's do some more conceptual questions. Is there a vertex for which the shortest paths tree from that vertex is the same as the Prim MST in this graph? I'll give you a second to think about it. Okay, let's see. The answer is yes, and it's in this specific shortest path, or in this specific minimum spanning tree, there are actually 3. So let's explore one of these cases. So let's maybe do B. So going back to the minimum spanning tree here, the shortest path from B to G is the only path from B to G, so that's definitely the same. So going to A, our options are going straight to A or going maybe through C. I think any other path is more obviously incorrect. So if you look, going through C will inherently take longer because this edge is 12. So our direct path that we already have in the MST is our best bet. Likewise, going to C, going through A, or going through E will inherently take longer. So this is also already the shortest path from B to C. Looking at E, likewise, going through F will take longer and going through C will take longer. So this is the shortest path from B to E. And going through E is actually faster than going directly to F because this takes 6 and this takes 7. So this is the shortest path from B to F. Lastly, going to D, there's only one path to D. It has to go through C. And we already figured out what the shortest path to C is, so this is also correct in our minimum spanning tree. Of course, this is not the case for everything. For instance, for C, this isn't the case. The shortest path from C to everything is not included in our MST because the path from C to E directly is only 6, but going through B takes 7. However, in our MST, we have these two lines and not this line included. Okay, next, true or false? Adding 1 to the smallest edge of a graph with unique edge weights must change the total weight of the MST. What do you think? Okay, so in this case, it's true. Okay, so there's two possible cases that we can think about. Either this is the smallest edge and it stays the smallest edge even once we add 1, which will increase the weight by 1 naturally, or some edge that was previously larger but is no longer larger takes its place. And in that case, there is no other edge of equal, since there's no other edge of equal weight, this can be the case, this will increase the weight by less than 1. If there were other edges of equal weight, then this no longer applies because it is possible that once you increase 1, you'll just switch over to an edge that is the same weight that you used to have. Okay, another one, the true or false. The shortest path from vertex A to vertex B in graph G is the same as the shortest path from A to B using only edges on T, where T is the MST of G. So we've kind of gone over this already, but true or false? I mean, yeah, it is true for literally vertices A and B in this graph, but it isn't true for all vertices in this graph, right? It isn't true for C like we talked about, or E. Okay, so next, given any cut, the maximum weight crossing edge is the same, the maximum weight crossing edge is in the MST. This is true, and the reason is because there's a thing called a cut property proof, which basically means that if you cut a graph in any way, for instance, let's take this graph and we cut it, the minimum edge that spans that cut, so in this case there are 4 edges, there's a 9, the 6, the 4, and the 7, this minimum edge will guaranteed to be in our minimum spanning tree, which is just a fact. Likewise, if we do the same thing, but we flip it and say the largest edge will be in our maximum spanning tree, the same proof can apply. Okay, let's move on to shortest paths. So first, let's do some mechanical running Dijkstras on this graph, starting from node A. Okay, so in this case, here is sort of this array that you will set up. So what this refers to is, this is kind of our priority queue. So we have our vertices and we have the distance from A to each of these vertices. So when we start off in our first iteration, we're on node A and we only have the distance, we only know that A to A is 0. Everything else we don't know yet because we haven't visited it. So we're gonna pop A off of our priority queue, thereby locking this in place. So this value will no longer change for the rest of these iterations. We pop A and we're gonna update the values for both of its children. So B gets updated and D gets updated. Now we're gonna pick the smaller of the two children and pop that as well. So we're gonna pop D first. And again, once we pop D, this value gets locked in for the foreseeable future. So we're gonna pop D and we're gonna update both of D's children. So E gets updated with 9, which is a sum of how long it takes to get to D, plus the distance between D and E. So that's 9. And likewise, we do the same thing for C. And next, we're gonna pop the next smallest item, which is going to be D, or it's gonna be B. So we're gonna pop B, locking it in place, and we're gonna update both of its kids. Now, the distance from going through B to get to C is the same as doing it through D. So this distance doesn't actually change, but the distance to get to E does change, right? Because before it was 9, but if you go through B, it's only 8. So we're gonna update this value before we pop C and lock that in place. And again, we're going to make sure that there's no better values for its children, but there is. So C gets updated right here. It used to take 8 to get there by going through B, and now if you go through B and C, it only takes 7. And then once you've done that, you're gonna pop E, and you've popped all of the vertices. So this is the final distance, the shortest distance to get from each node to every other node, or to get from A to every other node. Now here's a more conceptual question. What must be true about Dijkstra's to guarantee that we return the shortest path? Draw an example where this fails. Okay, so going over this, here's an example where this fails. In this case, we have this negative number, which is not allowed in graphs that we want to run Dijkstra's on, and here you can see why. So first, you're going to pop A, and you're gonna have two values, right? You're gonna have the value for B and for C. Now C is going to have a distance of 1, and B is going to have a distance of 100, which is way bigger. So we're going to pop C next, and we're going to update the value of D. So D is going to have a distance of 2, while B still has a value of 100. So we're going to continue, pop D, update the value for E. E is going to have a value of 3, while B still has a value of 100. So we're going to pop E, and now we have our shortest paths tree for every node except B. So we finally pop B, and we're done. But there is a faster way to get to D, right? If we went from A through B to D, then our distance would be negative 100 instead of 2, which is a better number. But because of the fact that Dijkstra doesn't really account for negative values, this doesn't work. Okay, last problem. Let's do A-star search. So here's more first mechanical problem. So I'll give you guys a chance. Okay, so this is the sort of chart you get here. And in this chart, I've listed it such that the first number is the actual distance from A to that node. And the second number is that distance plus the heuristic that guesses the distance from that node to G. So you can kind of imagine it as this is the actual distance to that city, and this is our prediction for how long it will take us to get to our target if we go through that node. So first, we're going to start with A. A is a distance of 0 to itself. However, it has a heuristic of 8. So in doing that, we're going to pop A first, and we're going to update both of its kids. So B is 1 away, D is 2 away, and then we're going to add their heuristics to those values to get that actual priority value. So we're going to pop B first, and then we're going to update the value of C. So C's actual distance from A is 4, and we're going to add 5 to that to get the heuristic value. So here we have 4, 9, and 2, 8. So we're going to pop 2, 8 right now, and because 8 is smaller, so we're going to pop D. And in doing that, we have to update the value for E. So E is 5 away from A and has a heuristic of 3. So we have that value of 8 down here, 5. Here is a great example that you can see that the actual distance doesn't matter. The heuristic, the distance plus the heuristic is what actually matters. So we're going to pop the value with the lower value here, even though it has the higher value right here. So we're going to pop E now, and then going from E, we have a straight shot at G, which it takes 8. Now, obviously, G has a heuristic of 0 to get to itself, because once you get to G, you're already there. So we have a final value of 8, and at this point, we pop G, and we're done. We found our shortest path. It takes 8. We're not even going to keep exploring this upper value. Now, is this heuristic admissible? I'll give you a chance to think about it. No, it's not, because the heuristic of C is 5, but the shortest path from C to G is 3. And if you remember, we said that heuristics always have to be less than or equal to their actual distance. And the reason is that we actually got the incorrect answer in the previous problem, right? The actual shortest path is going through here. It would have this actual distance of 7, which is smaller than 8. And that's what happens when your heuristic is not admissible. Okay, so we got through this. That's the last problem, and good luck, guys. Bye.